Settle in, let your breath slow. Tonight we're going to drift together through something beautiful and strange, something that sounds simple but opens into infinity. A light year, just two small words, but within them, the entire cosmos waiting. You've heard this term before, haven't you? Scientists say it casually, 4 light years away, millions of light years distant, as if these are just numbers, just measurements, but they're not, they're doorways. They're invitations to see the universe differently, to feel your place within it, to understand that distance and time are woven together in ways that change everything. By the time we finish this journey tonight, something will have shifted in you. The stars won't look the same. The darkness between them won't feel empty. You'll carry with you a sense of the cosmic ocean we're all floating in, and perhaps, just perhaps, you'll feel a little less alone in it. But first, let's breathe. Let's begin where we are, here, now, in this moment. The familiar ground beneath our feet, distance. It's something you understand intimately, isn't it? You know the walk to your favorite cafe, the way the light changes as you turn the corner, the smell of bread from the bakery you pass, the number of steps it takes, maybe 300 steps. Maybe 10 minutes. This is distance as you've always known it, measured in footsteps, in time, in the rhythm of your breathing. A kilometer is about a 12-minute walk at a comfortable pace, not rushing, not dawdling, just walking the way humans have walked for hundreds of thousands of years. Your ancestors knew distances this way, to the water source, to the hunting grounds, to the next valley where the berries grew thick in summer. These measurements are woven into your body. Your muscles know them. Your sense of time knows them. When someone says the store is 5 kilometers away, your mind doesn't just calculate, it feels the journey. You picture it, maybe 15 minutes by car. Maybe you'll hit that one traffic light. Maybe you'll see the old tree that's been there forever, standing like a patient guardian. This is human-scale distance. This is the world we evolved to understand. But let's walk a little farther in our minds. From New York to Los Angeles, about 4,500 kilometers, still comprehensible. A 5-hour flight. You've probably made journeys like this, or know people who have. You cross a continent. You watch the landscape transform beneath you, cities giving way to farmland, farmland to mountains, mountains to desert, desert to ocean. The journey is long, yes, but it's achievable. Humans do this every single day. The Earth's circumference at the equator is about 40,075 kilometers. Now we're talking about something bigger, but still, Ferdinand Magellan's expedition sailed around the world. It took 3 years, from 1519 to 1522, but it was possible. The Earth is vast from our perspective, standing on its surface, but it's finite. It has edges we can reach. It's a world we can, theoretically, explore completely. But then we step beyond, the first leap into strangeness, the moon, our closest celestial companion, the gentle light that's watched over every human who's ever lived, the subject of countless poems, countless songs, countless moments of wonder. It's 384,000 kilometers away. Let that settle for a moment. 384,000 kilometers. Your mind tries to picture it and can't quite, can it? It's not like driving across the country anymore. It's not like sailing around the world. There's no road, no landmarks, no rest stops, just distance. Pure, empty distance across the black. When the Apollo astronauts journeyed to the moon, it took them about 3 days. 3 days traveling at about 11 kilometers per second, roughly 39,600 kilometers per hour. That's nearly 400 times faster than highway driving. Imagine that speed. Imagine the fuel burning, the rockets screaming, the Earth shrinking behind you. And even at that incredible velocity, a speed no human had ever experienced before, it still took 3 days. 3 days to reach something you can see with your naked eye. Something that feels so close, hanging there in the night sky like a pearl. You can see craters on its surface with a pair of binoculars. It's right there. And yet, 3 days of traveling through the void, this is where our intuition starts to fail us. This is where the familiar mathematics of distance begin to fracture into something stranger. The sun's embrace now. Let's go farther. Let's go to the sun. 150 million kilometers. Your brain sees that number and what does it conjure? Probably nothing concrete. It's too big. It's abstract. It's just a number floating in space, disconnected from anything you can touch or feel or walk. But let's try to ground it. Let's try to make it real. At the speed of those Apollo spacecraft, 11 kilometers per second, it would take about 160 days to reach the sun's distance. Over 5 months of continuous travel at speeds that would tear through the atmosphere like thunder, 5 months of burning through the dark, and you'd just be reaching the distance to our star, the sun. the source of all light, all warmth, all life on Earth. The star we see every morning, the presence we feel on our skin, the giver of days and seasons. It's 150 million kilometers away. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. This means something profound, something that should make you pause. You have never seen the sun as it is right now. Never, not once in your entire life. Every sunrise you've ever watched, you were seeing the sun as it was 8 minutes ago. Every sunset, every moment of sunlight warming your face, every shadow cast on a summer afternoon, all of it is light that left the sun over 8 minutes before it touched you. If the sun suddenly vanished, just blinked out of existence, we wouldn't know for 8 minutes. For 8 minutes and 20 seconds, the world would continue as normal. Birds would sing, people would walk their dogs, children would play, the sky would be bright and blue, and then, suddenly, darkness. Sudden and total and terrifying darkness as the last light from a dead star finally exhausted itself. The moon, when you look at it, you're seeing it as it was 3 seconds ago. Not much of a delay, true, but still a delay. When astronauts on the moon spoke to mission control in Houston, there was always this pause, this lag. The astronauts would say something, 3 seconds of silence. Mission control would hear it, they'd respond. Another 3 seconds of silence, then the astronauts would hear the response. You can hear it in the recordings, that strange, haunting pause, that reminder that even at the speed of light, the fastest thing in the universe, distance takes time to cross. When kilometers lose their meaning, Mars, at its closest approach, is about 54 million kilometers away, at its farthest. About 401 million kilometers. The distance changes constantly as both planets orbit the Sun, sometimes on the same side, sometimes on opposite sides. When NASA operates rovers on Mars, Curiosity, Perseverance, these remarkable machines exploring an alien world, there's always a communication delay. Between 3 minutes and 22 minutes, depending on where Mars is in its orbit. Think about what that means. You can't drive a Mars rover in real time. You can't react to obstacles instantly. You can't steer around a rock the moment you see it. Instead, engineers on Earth must plan carefully. They study images from previous days, they plot a route, they write a sequence of commands, they send those commands to Mars, they wait, and if something goes wrong, if the rover gets stuck, if it encounters an unexpected obstacle, they have to wait again. Wait for the information to reach Earth, wait while they analyze the problem, wait while they write new commands, wait while those commands travel back to Mars. A problem that might take seconds to solve on Earth can take an hour or more to solve on Mars. And Mars is our neighbor, Mars is close. Saturn with its magnificent rings, its moons like worlds unto themselves. Saturn is about 12 billion kilometers away at its closest approach, about 12 light hours. The Cassini spacecraft orbited Saturn from 2004 to 2017, sending back images that took our breath away. Pictures of the rings in stunning detail, close-ups of moons like Titan and Enceladus, views that no human eye had ever seen before, but every image took over an hour to reach Earth. Over an hour from the moment Cassini clicked the picture to the moment scientists saw it, and this meant Cassini couldn't be controlled in real time. Engineers couldn't watch what the spacecraft was seeing and adjust on the fly. They had to program entire sequences of commands days or weeks in advance, upload them to Cassini, and then trust that the spacecraft would execute them correctly, trust that nothing would go wrong. Because if something did go wrong, by the time Earth knew about it and sent new commands, over 2 hours would have passed. 2 hours is a lifetime when you're flying through space at thousands of kilometers per hour. The edge of our reach, Voyager 1. Launched in 1977, nearly 50 years ago as I speak to you tonight, and it's still out there, still traveling, still sending back whispers of data from the edge of the solar system. It's about 24 billion kilometers from Earth now, about 24 light hours away. For nearly 5 decades, it's been moving at about 17 kilometers per second, about 61,200 kilometers per hour. At that speed, you could cross the entire United States in about 2 minutes. And yet, after nearly 50 years of constant travel, Voyager 1 still hasn't traveled 1 full light day from Earth. 1 light day, 24 light hours, about 26 billion kilometers. This is roughly where the heliosphere ends, that bubble of space where the sun's influence dominates, where the solar wind streams out from our star and pushes against the thin gas of interstellar space. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to enter interstellar space. It was a historic moment, a triumph, a milestone in human exploration, and yet, it's still right here, still in our cosmic backyard, still, cosmically speaking, at our doorstep. Out at one light week, about 181 billion kilometers, nothing human-made has ever been. Nothing will be for decades, maybe centuries. Out there, the sun would no longer be the overwhelming presence it is from Earth. It would appear as just a bright star, brighter than others certainly, but just a point of light in an ocean of darkness. If you were out there, floating in that immense silence, you'd see the sun as one star among thousands. You'd realize, perhaps for the first time with full visceral understanding, that our sun is not special. It's not unique. It's just one light among countless others, all scattered across the infinite dark. The light year reveals itself, and so we arrive here, at the threshold. At the place where we must abandon our familiar measurements and embrace something new. A light year. It's not a measure of time, despite the word year in its name. It's a measure of distance. The distance that light, the fastest thing in the universe, the speed at which causality itself propagates through space, travels in 1 year. Light moves at 300,000 kilometers per second. Every single second, light crosses 300,000 kilometers. In the time it takes you to blink, light could circle the Earth 7.5 times. In 1 second, light could travel from New York to Los Angeles and back 37 times. This speed is almost impossible to visualize because nothing in our daily lives moves anywhere near that fast. The fastest commercial airplane travels at about 900 kilometers per hour, about 0.25 kilometers per second. Light moves over 1 million times faster than that. Even the Parker Solar Probe, the fastest spacecraft humanity has ever built, travels at about 192 kilometers per second at its peak, and that's still only about 0.64% the speed of light. By human standards, it's screaming through space, but compared to light, it's barely crawling, so. Light travels at 300,000 kilometers per second. There are 60 seconds in a minute, 60 minutes in an hour, 24 hours in a day, 365 days in a year. Multiply it all together, 300,000 times 60 times 60 times 24 times 365. You get approximately 9.46 trillion kilometers. To be precise, 9,460,730,472,580. 8 kilometers, but let's just say 9.46 trillion, that's 1 light year. That's the distance light travels in 1 year of continuous motion at the fastest speed the universe allows. And this is the number we're going to live with tonight. This is the distance we're going to try to understand, not with our calculating minds, but with something deeper, with our sense of wonder, our capacity for awe, our ability to sit with vastness and let it change us. What does a trillion really mean? But first, we need to talk about what a trillion actually is, because most of us have no intuitive sense of this number. We throw around million, billion, trillion as if they're similar, just increasingly large numbers, but they're not similar at all. The gaps between them are staggering. A million seconds is about 11.5 days. You can imagine that, less than 2 weeks. You've lived through periods of 11 days many times. You know what that feels like, the rhythm of it, the passage of time, the way days accumulate into weeks. A billion seconds is about 32 years. Now we're talking about a significant portion of a human lifetime. If you started counting seconds when you were born and counted continuously, never sleeping, never eating, never stopping, you'd be 32 years old when you reached 1 billion. A trillion seconds is about 31,700 years. Let that wash over you. 31,700 years. That's longer than all of recorded human history. Agriculture was invented about 10,000 years ago. Before that, all humans everywhere lived as hunter-gatherers, following animal herds, gathering seasonal plants, moving with the rhythms of nature. Writing appeared about 5,000 years ago. The pyramids were built about 4,600 years ago. To count to 1 trillion, you'd need to have started counting before any of that happened. You'd need to have been counting when humans still lived in small tribal groups. When there were no cities, no nations, no permanent settlements, when we had barely begun to shape the world around us. 31,700 years ago, we were living in the last ice age. We were hunting woolly mammoths. We were just beginning to spread across the globe, leaving Africa and populating Europe and Asia. There was no written language, no complex art beyond simple cave paintings. No technology beyond sharpened stones and wooden spears. That's how long a trillion seconds is, and a light year is 46 trillion kilometers. Each one of those kilometers is a real distance. The distance you could walk in about 12 minutes at a normal pace, and there are 46 trillion of them stacked end to end, stretching across space. Our brains didn't evolve to handle numbers like this. We evolved to count members of our tribe, animals in a herd, days until the seasons changed. We can count to a few hundred, maybe a few thousand if we concentrate, but 946 trillion, that's so far beyond our cognitive capacity that it might as well be infinity. And yet it's not infinity, it's a specific distance, it's real, building up to the light year, so let's build up to it slowly. Let's take this journey step by step, moving from the familiar to the unfamiliar, watching as each distance we comprehend becomes tiny compared to what comes next. 1 light second is 300,000 kilometers. That's roughly the distance from Earth to the Moon, and about 3/4 of the way back. In 1 single second, light makes that entire journey. The moon that hangs in your night sky, light reaches it in just over 1 second. 1 light minute is about 18 million kilometers, roughly 12% of the distance from Earth to the Sun. If you could somehow stand on the Sun, which you can't, of course, it's a ball of plasma with surface temperatures around 500 degrees C, you'd be seeing Earth as it was over 8 minutes ago. If Earth suddenly exploded, the Sun wouldn't know for over 8 minutes. The event would happen, the planet would be gone, but the light carrying that information would still be crossing the void between worlds. This has practical implications. When NASA's Perseverance rover explores Mars, every command from Earth takes between 3 and 22 minutes to arrive, depending on where Mars is in its orbit. And any data the rover sends back takes the same amount of time to reach Earth. You can't drive it in real time. You can't react instantly. You have to plan, wait, trust, hope. 1 light hour is about 1/8 billion kilometers. Saturn, at its closest, is about 1-2 light hours away. When Cassini was orbiting Saturn, taking those breathtaking photographs, there was over an hour of delay between when it captured an image and when that image reached Earth. Over an hour for light, the fastest thing in existence to cross the distance. 1 light day is about 26 billion kilometers. Voyager 1, after traveling for nearly 50 years, is about 1 light day from Earth. After 5 decades of constant motion through the vacuum of space, moving faster than anything else humanity has launched, it's traveled 1 day's worth of light's journey. 1 light year is 365 of those light days. It's 8,760 light hours. It's 525,600 light minutes. It's 31,536,000 light seconds. See how the numbers multiply, how quickly we scale up. We started with 1 light second, already an enormous distance by human standards, and we've multiplied by 60, then 60 again, then 24, then 365, and we're just now reaching 1 light year. 46 trillion kilometers, that's what we're trying to understand tonight. Why astronomers need the light year. Imagine if astronomers used kilometers for everything. Proxima Centauri, the nearest star to our sun, is about 14 trillion kilometers away. That's awkward, hard to remember. Doesn't give you any intuitive sense of the distance. But if I tell you Proxima Centauri is 424 light years away, something clicks. The number is cleaner, more manageable, and it carries meaning. If one star is 4 light years away and another is 40 light years away, you immediately know the second is 10 times farther. You can compare. You can build intuition. More than that, light years connect distance and time in a profound way. When you look at a star that's 4 light years away, you're seeing light that left that star 4 years ago. You're not seeing the star as it is now. You're seeing the star as it was. You're looking into the past. This connection becomes crucial for understanding the universe. The farther we look in space, the farther back in time we see. The most distant galaxies we can observe are billions of light years away, which means we're seeing them as they were billions of years ago, when the universe was young, when stars were just beginning to form in great cosmic nurseries of gas and dust. The speed limit of the universe. The speed of light isn't just fast, it's the speed limit of the universe. Nothing can go faster. This isn't a technological limitation we might overcome with better engineering or more powerful rockets. It's a fundamental law of physics woven into the very structure of spacetime itself. Einstein's theory of special relativity, published in 1905, showed us why. As objects approach the speed of light, strange things happen. Time slows down for the moving object relative to stationary observers. This is called time dilation. The object's mass effectively increases, or more precisely, its inertia increases. It becomes harder and harder to accelerate. The energy required to continue accelerating increases without limit. To actually reach the speed of light would require infinite energy, which is impossible. Therefore, nothing with mass can reach the speed of light. Only massless particles like photons, the particles of light itself, can travel at light speed, and photons must always travel at light speed. They can't slow down or speed up. From the moment they're created to the moment they're absorbed, they move at exactly 300,000 kilometers per second. No faster, no slower. This has been tested countless times: particles in accelerators, GPS satellites orbiting Earth, cosmic rays from deep space. Every test confirms it. Time dilation is real. The speed of light is absolute. The universe has a speed limit, and it's not negotiable. Our nearest stellar neighbor, Proxima Centauri, is 24 light-years away, about 14 trillion kilometers. It's a small red dwarf star, about 1/8 the Sun's mass and 1/7 its diameter. It's so small and dim that you can't see it with your naked eye, even though it's our nearest stellar neighbor. You need a telescope to spot it. If you could travel at the speed of our fastest spacecraft, the Parker Solar Probe, at 192 kilometers per second, it would take about 6,800 years to reach Proxima Centauri. 6,800 years, longer than all of recorded human history. Writing was invented about 5,000 years ago. You could have started your journey when humans first learned to write, traveled continuously at the fastest speed any human spacecraft has ever achieved, and you'd still be traveling today. There have been proposals for faster spacecraft. Breakthrough Starshot, announced in 2016, proposes using powerful ground-based lasers to accelerate tiny spacecraft, essentially computer chips with cameras attached to ultra-thin light sails, to about 20% of light speed. At that speed, a probe could reach Proxima Centauri in about 20 years. Add another 4 years for the signal to travel back to Earth, and you could potentially get data from our nearest stellar neighbor in 24 years. 24 years, within a human lifetime. You could launch the mission when you're young and potentially see the results before you die. But the engineering challenges are enormous. You need lasers with the combined power of about 100 nuclear power plants. You need to protect the spacecraft from collisions with interstellar dust. At 20% of light speed, even a speck of dust hits with the energy of a large bomb. You need communication systems powerful enough to send data back across 4 light-years of space. And you need to aim perfectly at those speeds. You cross the entire inner solar system in hours. You get one shot, no slowing down, no second chances. Even if we could build such a spacecraft and successfully send it, it would be at least 20 years before it reached Proxima Centauri, and another 4 before we received any data. That's 24 years round trip for information, assuming everything works perfectly. And that's just to reach our nearest stellar neighbor. Looking into the past, when you look up at the night sky, you're not seeing stars as they are, you're seeing them as they were. Sirius, the brightest star in the night sky, is 6 light-years away. When you look at Sirius tonight, you're seeing light that left that star 6 years ago. If you're 20 years old, you're seeing Sirius as it was when you were about 11, probably in middle school. If you're 40, you're seeing it as it was in your early 30s. Vega is about 25 light-years away. If you're 25 years old and you look at Vega tonight, you're seeing light that left that star the year you were born. Betelgeuse, the red supergiant in Orion's shoulder, is about 550 light-years away. The light you see from Betelgeuse tonight started its journey in the year 1475, during the Italian Renaissance, before Columbus sailed to the Americas, when Leonardo da Vinci was 22 years old. The Byzantine Empire had fallen 22 years earlier. The printing press had been invented only about 20 years before. Most of Europe was emerging from the Middle Ages. The modern world didn't exist yet, and the light from Betelgeuse that reaches your eye tonight has been traveling through space for over 550 years. Here's the beautiful, haunting thing. Betelgeuse is a massive star nearing the end of its life. At some point in the relatively near future, within the next 100,000 years or so, it will explode as a supernova. When it does, it will briefly shine as bright as the full moon, visible even during the day. But here's the question that should make you pause: has it already happened? Maybe Betelgeuse exploded in the year 1600 or 1700 or 1800. We wouldn't know. We couldn't know. The light from that explosion would still be traveling toward us, taking 550 years to make the journey. The star could already be gone, destroyed in a catastrophic explosion, and we'd still see it shining peacefully in the sky for centuries to come, completely unaware that we're seeing a ghost, an echo of something that no longer exists. Polaris, the North Star, is about 445 light-years away. When its light began traveling toward us, Jamestown hadn't been founded yet. The Pilgrims hadn't arrived at Plymouth Rock. Shakespeare had just begun writing his plays. He hadn't yet written Hamlet or Macbeth. The United States wouldn't exist for another 180 years. And tonight, that ancient light enters your eye. You're connected across space and time by photons that have been traveling for 4.5 centuries. Our stellar neighborhood within about 20 light-years of Earth, there are approximately 130 known star systems. Some are single stars like our Sun. Others are binary systems, 2 stars orbiting each other in an eternal gravitational dance. Some are triple systems like Alpha Centauri. Barnard's star, about 6 light-years away, is the second closest star system to Earth. It's another red dwarf, small and dim. What makes it interesting is that it's moving toward us relatively quickly by stellar standards. In about 10,000 years, it will be closer to Earth than Proxima Centauri is now, becoming our new nearest stellar neighbor. But even at its closest approach, it will still be nearly 4 light-years away. The distances between stars are so vast that even when they're moving toward each other, even when they're approaching at tens of kilometers per second, it takes thousands of years for that motion to make any noticeable difference. Sirius, 86 light-years away, is actually a binary system. Sirius A is a bright white star about twice the Sun's mass. Sirius B is completely different. It's a white dwarf, the dense remnant of a star that exhausted its nuclear fuel and collapsed. White dwarfs are fascinating objects. They're about the size of Earth but have the mass of a star. Sirius B has roughly the Sun's mass compressed into a sphere about the size of our planet. A teaspoon of material from Sirius B would weigh about 5 tons on Earth. The 2 stars orbit each other every 50 years, locked together by gravity, each following an elliptical path around their common center of mass, a cosmic ballet that's been going on for billions of years and will continue for billions more. Our galaxy, the Milky Way. The Milky Way contains between 100 billion and 400 billion stars. That's a huge range because it's actually quite difficult to count stars in our own galaxy. We're inside it. It's like trying to count trees while standing in the middle of a vast forest. Dust blocks our view in many directions. Dim stars are hard to detect. The galaxy is so large we can't see all of it at once from our position, but the best estimates suggest around 200 to 300 billion stars. Our Sun is just one of them. An ordinary yellow dwarf of average size and brightness. There's nothing special about it from a galactic perspective. It's not the biggest, not the brightest, not the hottest, not the coolest, just typical, average, one among hundreds of billions. We're located in one of the spiral arms, about 26,000 light-years from the galactic center. 26,000 light-years. The light we see from the center of our galaxy, if we could see through all the dust, left the galactic center 26,000 years ago. When that light began its journey, humans were still living as hunter-gatherers in the Stone Age. Agriculture hadn't been invented. There were no permanent settlements, no cities, no civilization as we understand it. Everything we think of as human civilization, from the first farms to the first cities to the first writing to all the ancient empires to the modern world, all of it has happened while light from the galactic center was traveling toward us. The Milky Way is roughly 100,000 light-years across. If you could somehow travel at the speed of light, which you can't, it would take you 100,000 years to cross the galaxy from one side to the other. Modern humans, Homo sapiens, are about 300,000 years old as a species. You could have started crossing the galaxy when the first modern humans appeared in Africa, traveled at light speed for 100,000 years, and you'd only be 1/3 of the way across. The Sun orbits the galactic center at about 230 kilometers per second. That's fast. At that speed, you could circle Earth in just under 3 minutes. But even at this incredible speed, it takes the Sun about 225 to 250 million years to complete one orbit around the galaxy. The last time the Sun was in its current position, dinosaurs were just beginning to evolve on Earth. Since then, dinosaurs evolved, ruled the planet for over 160 million years. When extinct, mammals took over, humans eventually evolved, and the sun has only just now returned to approximately the same spot in the galaxy. One galactic year, one cosmic season, worlds beyond our own. One of the most exciting developments in recent decades has been the discovery of exoplanets, planets orbiting stars other than our sun. Until 1992, we knew of only one planetary system, our own. We suspected other stars might have planets, but we had no direct evidence. Then came the discoveries. First around a pulsar in 1992, then around a sun-like star in 1995, and since then, the floodgates have opened. As of 2024, we've confirmed over 5,000 exoplanets, with thousands more waiting to be verified. The TRAPPIST-1 system, about 40 light-years away, contains 7 Earth-sized planets orbiting a small red dwarf star. 3 of them are in the habitable zone, the region where temperatures might allow liquid water to exist on the surface, 40 light-years away. When we observe TRAPPIST-1 today, we're seeing it as it was in 1985. If there's intelligent life on one of those planets, and if they developed radio technology and started broadcasting signals, those signals would take 40 years to reach us. We'd be receiving broadcasts from 1985. And if we detected such a signal and responded, it would take another 40 years for our reply to reach them. They'd hear our answer in 2065, an 80-year round trip for a single exchange of information. You could ask a question and die of old age before receiving an answer. The problem of communication across light years, this is one of the most challenging and sobering aspects of cosmic distances. It fundamentally changes what communication means. Imagine trying to establish contact with a human settlement on a planet orbiting Proxima Centauri, 424 light-years away. You send a message, how are things, how are the crops, is everyone healthy? That message travels at light speed for 424 years. 4 years, 2 months, and about 20 days later, your message arrives. If they respond immediately, their answer takes another 424 years to reach you. That's over 8 years for a single exchange. You could ask about their latest harvest and receive an answer about crops that were eaten 4 years ago. You could ask how a sick person is doing and receive news of their death years after it happened. You could send advice or help, but by the time it arrives, the situation will have changed completely. Any kind of real-time conversation, the immediate back and forth we take for granted, is completely impossible. Conversations would span years, debates would take decades, a diplomatic negotiation could take a century or more. This has profound implications for governance and society. A colony 4 light-years away couldn't be governed from Earth in any meaningful sense. Any laws or directives sent from Earth would arrive years out of date. The political situation on Earth could change completely between when a message was sent and when it arrived. The colony would need to be autonomous, self-governing, making its own decisions on everything from resource allocation to conflict resolution to emergency response. Because waiting years for approval on every decision would be impossible, over time, the colony and Earth would drift apart culturally. They'd develop their own customs, their own ways of life, their own solutions to problems. They'd be connected by letters from the past, but unable to maintain the immediate, ongoing connection that holds societies together. Over generations, they might become so different that they'd barely recognize each other. They'd share a common origin, a common history up to the point of separation, but from that point forward, they'd diverge, evolving separately like species isolated on different islands. For more distant stars, it gets worse. A settlement 10 light-years away would have a 20-year communication delay. Messages you send to your children there would reach them when they're adults. Their responses would return when your grandchildren are grown, when you might be dead. A civilization 100 light-years away would have a 200-year communication delay. Neither you nor your children nor your grandchildren would live to see a reply. Only your great-great-great-grandchildren might hear back. The conversation would span generations, each generation sending messages to strangers they'd never meet, receiving messages from people long dead. Time dilation and the traveler's paradox. There's another strange implication of traveling near light speed, one that continue 1931 Einstein's theory predicts and experiments have confirmed: time dilation. As you approach light speed, time slows down for you relative to stationary observers. The faster you go, the more extreme this becomes. Imagine a spacecraft that could reach 99% of light speed. You board it and travel to a star 10 light years away, then turn around and come back. From Earth's perspective, this journey takes about 20 years, 1 years each way, but because of time dilation, you would age much less. At 99% of light speed, time passes about 22 times slower for you. While 20 years pass on Earth, you'd only experience and age about 11 months. You'd step off the spacecraft having aged less than a year, while everyone you knew aged 20 years. Your younger sibling might now be older than you. Your children, if you had any, might now be adults older than you are. You've traveled into their future. At even higher speeds, 99% of light speed, you could travel to a star 100 light years away and back. From Earth's perspective, this takes over 200 years, but from your perspective, due to extreme time dilation, the journey might take only a few years. You'd return to Earth over 200 years in the future. Everyone you knew would be long dead. The world would be completely different, politically, technologically, linguistically. You'd be a time traveler, but you could never go back. The observable universe lets zoom out even farther. Let's look at the biggest distance scale of all. The observable universe is the region of space from which light has had time to reach us since the Big Bang. The universe is about 13.8 billion years old. Light has been traveling toward us for all that time. But here's the strange part: the observable universe is larger than 13.8 billion light years in radius. It's about 46.5 billion light years in radius, about 93 billion light years across. How is this possible? Because the universe has been expanding while the light was traveling toward us. Space itself has been stretching, carrying distant objects away even as their light traveled toward us. Within this observable universe are an estimated 2 trillion galaxies. Each galaxy contains billions or trillions of stars. Multiply it out, and the total number of stars in the observable universe is around 200 billion trillion. That's a 2 followed by 23 zeros. More stars than grains of sand on all the beaches on Earth. More stars than seconds have passed since the Big Bang. More stars than you could count if you spent your entire life doing nothing but counting. And we know from observations that most stars have at least one planet, so there are probably similar numbers of planets, maybe more. The universe is filled with worlds, more worlds than we could ever count, ever visit, even if we had unlimited time and unlimited technology. The structure of everything at the largest scales, the universe has structure. Galaxies aren't randomly scattered like grains of sand, they're organized. Galaxies cluster together in groups held by gravity. These clusters organize into superclusters, massive structures containing multiple galaxy clusters, and superclusters arrange themselves into filaments, enormous thread-like structures stretching hundreds of millions of light years across space. Between these filaments are vast voids, regions with very few galaxies. Empty spaces that can be hundreds of millions of light years across. The universe looks like a cosmic web, filaments of matter with vast emptiness between them. Islands of light separated by enormous oceans of darkness, and the universe is expanding. Space itself is stretching, carrying galaxies with it like raisins in rising bread dough. For nearby objects, this expansion is negligible. The space between Earth and the Moon isn't expanding, gravity holds them together. The space within our solar system isn't expanding. The space within our galaxy isn't expanding. But on larger scales, between galaxy clusters, the expansion becomes significant. Distant galaxies are receding from us as space expands between us. The farther away a galaxy is, the faster it's receding. And for galaxies far enough away, space between us is expanding faster than light can travel through it. This doesn't violate the cosmic speed limit because the galaxies aren't moving through space faster than light. They're sitting relatively still in their local space. But the space itself is expanding so rapidly that the distance between us grows faster than light could traverse it. It's like trying to walk forward on a treadmill that's moving backward faster than you can walk. You're walking at your normal speed, but you're moving backward relative to your starting point. This means there are regions of the universe moving away from us so fast that light from those regions will never reach us. Not in a billion years, not in a trillion years. Never. There's a cosmic horizon beyond which we cannot see. Not because the light hasn't had time to reach us yet, but because it never will. The expansion is carrying those regions away faster than light can close the gap. We are fundamentally, irreversibly cut off from those regions of the universe, the Fermi paradox and the silence of space. Given the vast number of stars and planets, given that the universe is 13.8 billion years old, given that life arose on Earth relatively quickly after conditions became suitable, it seems likely that life should exist elsewhere, perhaps even intelligent, technological life. And yet we've never detected any signs of alien civilizations. No radio signals, no laser pulses, no megastructures, nothing. The universe appears to be silent. This is called the Fermi paradox, after physicist Enrico Fermi, who famously asked, "Where is everybody?" The light year might be part of the answer. The distances between stars are so vast that they present enormous, perhaps insurmountable, barriers to communication and travel. Our radio signals have been leaking into space for about a century. They've reached all stars within roughly 100 light years. That sounds like a lot, but the Milky Way is 100,000 light years across. We've barely announced our presence to our immediate cosmic neighborhood, and even those signals are getting weaker as they spread out over larger and larger spheres. By the time our TV broadcasts reach a star a few dozen light years away, they're so faint they'd be almost impossible to detect above background noise. Any alien civilization trying to detect us would need extremely powerful radio telescopes pointed in our exact direction at the right frequency at the right time. And even if they did detect us and responded, we wouldn't hear back for decades or centuries, depending on the distance. Perhaps the universe is full of civilizations, but they're all so far apart that none of them ever make contact. Each develops alone, makes its discoveries alone, asks its questions alone, and eventually dies alone, never knowing if anyone else was out there. There's something melancholy about this possibility. We've evolved as social creatures. Connection is fundamental to who we are. The idea of being alone or of being surrounded by others but forever unable to reach them is profoundly isolating. But there's also something beautiful about it. It means every civilization that arises is precious. If we're alone, or effectively alone because we can't reach anyone else, then we carry a unique responsibility. We're the universe's way of knowing itself in this particular corner of space. The thoughts we think, the art we create, the science we discover, the love we feel, all of it is unique to us. We're not just one civilization among millions. We might be the only minds in our region of space for dozens or hundreds of light years in any direction. This makes what we do matter more, not less. What the light year means for us, so what does all this mean for you? How should you think about light years in your daily life? For most people, light years don't affect daily existence. You don't need to think about Proxima Centauri being 424 light years away when deciding what to have for breakfast or whether to take an umbrella. But there's value in occasionally stepping back and contemplating these scales. It provides perspective. When you realize that Earth is a small planet orbiting an ordinary star, that the nearest other star is over 4 light years away, that our galaxy contains hundreds of billions of stars, that there are trillions of galaxies in the observable universe, it changes how you see things. Your problems, whatever they are, exist on a tiny planet in a vast universe. That argument with a friend, that stress at work, that anxiety about the future, that disappointment, that frustration, all of it happens on one small world. The nearest star doesn't care about your problems. The galaxy doesn't notice. The universe continues its slow evolution, completely indifferent to human affairs. This isn't meant to diminish your experiences or suggest your problems don't matter. Your life matters to you, and that's what's important. Pain is pain, joy is joy, love is love. These things are real and important regardless of the scale of the universe. But sometimes when things feel overwhelming, when you're stressed or anxious or worried, it can help to remember the scale of things. You're living on a small planet orbiting an ordinary star in a vast cosmos. From that cosmic perspective, your problems are temporary, local, small, not unimportant, but small, contained, manageable. There's also something beautiful about understanding light years. When you look up at the night sky, you're not just seeing points of light, you're seeing stars that are light years away. You're seeing photons that have been traveling through space for years or centuries to reach your eyes. You're connected to those distant suns across vast distances of space and time. You're part of the universe, made of atoms forged in stars, looking up at other stars, understanding your place in the cosmic order. The future of exploration, as our technology improves, our ability to measure distances in light years becomes more precise. The Gaia spacecraft is creating the most detailed three-dimensional map of our galaxy ever made, measuring positions and distances of over 1 billion stars. Future telescopes will allow us to see even farther. The James Webb Space Telescope is already detecting galaxies over 13 billion light-years away. Future observatories might see even closer to the Big Bang, watching the first stars and galaxies form. We're also discovering more exoplanets every year. Many are dozens or hundreds of light-years away. We're mapping what exists at these vast distances. In the future, we might send robotic probes to nearby stars. Breakthrough Starshot is one proposal. Even if successful, probes would take decades to reach their destinations and more years to send data back. But barring revolutionary breakthroughs in physics, discoveries that completely overturn our understanding of space and time, light years will remain a fundamental barrier. The distances between stars are vast, the speed of light is finite. This isn't a problem to be solved. It's a fundamental property of the universe we live in. Coming back to Earth, for most of human history, the universe was small. Ancient people thought the stars were lights attached to a celestial sphere just beyond the moon. The entire cosmos was contained within a space you could reach if you climbed high enough. Even when we realized stars were distant suns, we had no sense of how distant. A few million kilometers, a few billion. The numbers were beyond our ability to measure, so they remained abstract. It wasn't until the early 20th century that we began to accurately measure stellar distances and realize how vast space truly is. When Harlow Shapley calculated the size of the Milky Way in 1918, showing it was about 100,000 light-years across, many astronomers were shocked. The universe was far larger than anyone had imagined. When Edwin Hubble showed in 1929 that spiral nebulae were actually distant galaxies millions of light-years away, the universe suddenly expanded again by orders of magnitude. Today we know the observable universe is 93 billion light-years across and contains about 2 trillion galaxies. This knowledge changes our perspective in fundamental ways. We're not at the center of the universe. We're not special in any cosmic sense. We live on a typical planet orbiting a typical star in a typical galaxy in a typical region of space. If you were transported to another galaxy billions of light-years away, you'd see a similar view, galaxies in every direction stretching to the horizon. The universe looks roughly the same from every vantage point. This is both humbling and empowering. Humbling because it shows how insignificant we are in cosmic terms. Everything we've ever done, every war, every empire, every discovery, has happened on one small planet in one small corner of one typical galaxy. But it's also empowering because it shows what we're capable of. We figured this out. We measured these distances. We understood our place in the cosmos. We're tiny, but we're also incredibly capable. We're conscious beings who can understand the universe that created us. That's remarkable. The weight of isolation, the beauty of connection understanding light years, forces us to confront difficult truths about space exploration and the future of humanity. The distances are so vast that they might represent fundamental barriers no amount of technological advancement can overcome. With current technology, reaching even the nearest star would take thousands of years. Even with revolutionary propulsion systems traveling at 10% of light speed, it would still take over 42 years to reach Proxima Centauri. Multi-generational ships have been proposed, massive vessels supporting populations for centuries, but the challenges are formidable. How do you maintain a closed ecosystem? How do you prevent genetic problems? How do you ensure descendants complete a mission their ancestors started? The reality is that interstellar travel with humans aboard might simply be impractical given the constraints of light speed and vast distances. We might be confined to our own solar system for the foreseeable future, perhaps permanently. That doesn't mean we can't explore with robotic probes, but human exploration of other stars might remain in the realm of science fiction. If intelligent life exists elsewhere, and many scientists think it probably does, the distances might make contact impossible even if civilizations survive for millions of years. Imagine an advanced civilization 50 light-years away. They've been broadcasting for a century, just like us. Those signals are passing through our region of space right now, but they're incredibly faint. Even if we detected them, think about what happens next. We'd be receiving signals from 50 years ago. If we responded immediately, our response would take another 50 years to reach them. A 100-year round trip for a single exchange. You could ask a question and die before receiving an answer. This fundamentally changes what contact means. There can be no dialogue, no conversation, no negotiation. Instead, it would be like exchanging encyclopedia entries, each civilization sending everything they know, hoping the other receives it. And both civilizations would need to survive and remain interested long enough for the exchange to happen. We've only been broadcasting for about a century. We don't know if we'll still be broadcasting in another century. Civilizations might rise and fall on timescales shorter than light travel time between stars. We might detect signals from civilizations that went extinct centuries ago, listening to radio echoes of dead worlds. There's also the possibility that the universe is full of civilizations, but they're so far apart that none ever make contact. Each develops alone, discovers alone, questions alone, and eventually dies alone, never knowing if anyone else was out there. The preciousness of this moment, and so we return here. To you, to this moment, to this breath. You're lying here or sitting here in the quiet of the night. You've journeyed with me across light years, across cosmic distances that dwarf imagination. You've seen stars billions of years old and galaxies trillions of kilometers away, and now you're back. Here now, this small moment, this small life, this brief flicker of consciousness on a small planet. From a cosmic perspective, you're insignificant. Your life is a blink, perhaps 80 or 90 years if you're lucky, in a universe 13. 8 billion years old that will continue for trillions of years more. But you're also remarkable. You're made of atoms forged in the hearts of stars that died billions of years ago. Stars that exploded, scattering their matter across space, matter that eventually coalesced into new stars, new planets, and ultimately into you. You're literally made of stardust. You're a way for the universe to know itself, to understand itself, to appreciate its own vastness and beauty. The thoughts you think, the art you create, the science you discover, the love you feel, all of it is unique, all of it matters. Because it's happening here and now, and it might not be happening anywhere else nearby. We might be the only minds for dozens or hundreds of light years in any direction. We're alone, but we're also important. We're small, but we're also precious. We're insignificant in cosmic terms, but we're also irreplaceable. When you look up tonight, so the next time you look up at the stars on a clear night, remember what you've learned. Those points of light are not just lights. They're distant suns, massive balls of fusing hydrogen, each potentially hosting its own system of planets and moons. They're light years away, separated from us by distances so vast that the light entering your eye has been traveling for years or centuries. Some of that light began its journey before you were born. Some of it left its star before your grandparents were born. You're connected to those distant stars across the vast distances of space and time, linked by light that has crossed the cosmic void to reach you. The universe is large beyond comprehension. You are small, a single person on a single planet, but you're here, and you can understand, at least conceptually, what a light year means. You can grasp that the universe is measured in these vast units. That space is filled with distances that dwarf anything in human experience. And that understanding, that ability to comprehend your place in the cosmos is extraordinary. It's what makes us human, what separates us from other life on Earth. We can look up and understand what we're seeing. We can contemplate infinity in our own smallness simultaneously. We can feel both humbled and empowered by the same knowledge. The gift of perspective, perhaps that's the most important thing to take away from understanding light years. Not just the technical definition, not just the mathematics of 46 trillion kilometers, but what it means for us as a species, for our future, for our place in the cosmos. We stand at a unique moment in history. We're the first generation to truly understand the scale of the universe. Our ancestors looked up at the same stars, wondered about the same questions, but they didn't have the tools or knowledge to measure the answers. They couldn't know that stars were distant suns. They couldn't know those suns were light years away. They couldn't comprehend the vast distances separating us from the rest of the universe. But we can. We've measured these distances. We've calculated them precisely. We know Proxima Centauri is 424 light years away. We know Andromeda is 25 million light years distant. We know the observable universe stretches 93 billion light years across. These aren't guesses. They're measurements backed by decades of careful observation. This knowledge changes us. When you truly understand that the nearest star would take thousands of years to reach with current technology, when you grasp that light from distant galaxies has been traveling for billions of years, when you comprehend that we might be fundamentally isolated by vast distances, it shifts your perspective on everything. It makes our differences seem smaller. The things we argue about, the borders we draw, the conflicts we engage in, all of it happens on one tiny planet in a vast cosmos. We're all together on this small world, separated from our nearest stellar neighbors by distances measured in light years. From that perspective, the things that divide us seem less important than what we share. The responsibility we carry, it also makes our existence more precious. If we're alone, or effectively alone because we can't reach anyone else across the light years, then what we do here matters enormously. We might be the only consciousness in our region of space, the only minds that can contemplate the universe and understand what they're seeing, the only beings who can create art, discover truth, feel love and compassion and wonder. That's a profound responsibility. It means we need to take care of this planet, this tiny island of life in the cosmic ocean. It means we need to preserve and protect the knowledge we've gained, the understanding we've developed. It means we need to think long-term. Not just about next year or next decade, but about the next century, the next millennium, the long future of humanity among the stars. More than distance, the light year is more than just a unit of measurement. It's a reminder of our place in the universe. A reminder that we're part of something vastly larger than ourselves, but also that we're unique and precious within that vastness. A reminder that stars are both incredibly far away and intimately connected to us through the light that bridges cosmic distances. Every time you look up at the night sky, you're participating in something ancient and profound. You're seeing across light years, you're looking back in time, you're witnessing the universe in all its glory. And you're part of that universe, made of the same atoms, following the same physical laws, connected by the same fundamental forces that govern everything from the smallest particle to the largest galaxy cluster. The meaning in mystery, that's what a light year really means. Not just distance, but connection. Not just isolation, but belonging. Not just our smallness, but our significance within that smallness. You don't need to fully comprehend it intuitively to appreciate what it represents. You can appreciate that the universe is vast beyond our ability to grasp. You can appreciate that light from distant stars has been traveling for years, decades, centuries to reach your eyes tonight. You can appreciate that we live in a tiny corner of an enormous cosmos, on a small planet orbiting an ordinary star in one galaxy among trillions. And in that appreciation, there's peace, there's wonder. There's a sense of being held by something larger than yourself, something that doesn't demand your understanding, only your awe. Rest now, so rest now. Let your breath slow, let your body relax. Let these thoughts settle like snowflakes, each one beautiful and unique and temporary. You've traveled far tonight, across distances measured in trillions of kilometers, across time measured in billions of years. You've seen stars being born and stars dying. You've witnessed the structure of galaxies and the expansion of space itself. And now you're back here in this body, in this moment, in this breath. The universe is vast, but you are here. The distances are incomprehensible, but you are present. The cosmos stretches on forever, but you are grounded in this single point in space and time, and that's enough. That's everything. You are small, but you are also infinite, because you contain the universe in your understanding, in your awareness, in your capacity for wonder. You are alone, but you are also connected to every star, every atom, every moment that has ever been and ever will be. You are temporary, but you are also eternal, because the atoms that make you have existed since the beginning, and they will continue long after you're gone, recycled endlessly through stars and planets and perhaps other forms of consciousness. So rest in that mystery. Rest in the knowledge that you don't need to understand everything. Rest in the beauty of being here now, alive, aware, part of the great cosmic story. The light from distant stars is still traveling toward us, carrying messages from the past, and you are here to receive it. Good night, traveler. Thank you for journeying with me through space and time. If this exploration has given you something, a moment of peace, a shift in perspective, a sense of wonder, then carry it with you. Remember, even though light years represent distances almost beyond comprehension, they're also what connect us to the stars. Every time you look up at the night sky, you're seeing across light years. You're seeing the universe, and the universe, vast as it is yours to contemplate. Good night, traveler. May you rest well, may you dream of stars, and may you never look at the night sky the same way again. The cosmos is within us. We are made of star stuff. We are a way for the universe to know itself. Breathe, rest, you are home.